3.2 is logarithmic functions. Within this lesson, we have 8 objectives, and because it is largely review of Algebra 2, actually I can't think of any part of it that we did not discuss in Algebra 2. I'm going to go through the objectives pretty quickly, and I'm going to talk to you about some relationships between the objectives, okay? All right. Logarithmic functions actually arise from exponential functions. We did exponential functions in Lesson 1. You remember from Lesson 1 that an exponential function is any function, in this case f of x, that is equal to b to the x power. So just because a function has an exponent does not make it exponential. A function is exponential when its exponent is or contains the variable. Okay, so where we get a logarithmic function, they developed out of mathematicians wanting to find an inverse for the exponential. The exponential function is a one-to-one function, meaning it passes both the vertical line test, making it a function, but it also passes the horizontal line test, which means that it's the same test, you just use a horizontal line, and the horizontal line would intersect the function at only one point at a time. If a function is one-to-one, that means that it does have an inverse, and we should be able to represent that inverse mathematically. So to find an inverse for our exponential, we switch the x and y, just like we've done, I believe it was chapter 1, and then we're supposed to solve this for y, but without logarithms, we don't have a method. We don't have a way to solve for an exponent that is a variable, and that's where y is. Y is in the exponent. So that's where logarithms come in. Okay, we have this definition of a logarithm. First of all, we set up this. This is for x's greater than 0 and b's greater than 0. Okay, and a b cannot equal 1. That should sound familiar from the exponential functions. All right, so what we do is we say that the log of x base b is equal to y. Y equals log x base b. Okay, for this log, x has to be greater than 0. And then every base has to be greater than 0 but not equal to 1. That is equivalent to b to the y equals x. Okay, I want you to remember where that comes from is we move the base, okay? We take the base of the log and we move it over to become the base of the exponent. So b to the y equals x. The base was moved. That's going to be the basis for objective 1. Writing an exponential function in logarithmic form, and objective 2, writing a logarithmic function in exponential form. Okay, so I switched those. Writing a logarithmic function in exponential form we're going to do first, okay? So, part A of example 1, 2 equals the log of x base 5. I want you to identify the base in part A, and I've identified them in red down here. Okay, so we have 2 equals the log of x base 5. So to put 2 equals log x base 5 into exponential form, that's where we're going to take the base and we move it over here, and it's actually going to pick up the 2. So it looks odd here, but it's 5 squared equals x. When you move the base of the log doesn't have a base to hold it up anymore. So the log goes away. That's just the way you can think about it. When we transition the base from the base of the log to the base of the exponent, there is no longer a log at all. So 5 squared equals x, or x is 25. Okay, it's probably what Math Excel is going to want. Okay, so when we come here, what's the base? The b, the subscript. We're going to move the b, and it's going to be b cubed equals 64. Okay? And then on part C, the base is the 3. This time we're going to move the 3 over to the right. So it's going to be 7 equals 3 to the y. Okay, that's just changing from logarithmic form into exponential form. Okay, one thing I want you to notice down here, it's interesting that here's your exponential form. We recognize this is the base, the b is the base, and the y is the exponent, the way that's written. When you transition into logarithmic form, b is still the base, this time it's a subscript, but the y is still called the exponent. Okay? A logarithm actually calculates an exponent value, even though we don't see superscripts. That's really what it's calculating. We're going to go to objective 2, change from exponential into logarithmic, and we can still rely on this chart to help us with that transition. Okay? So, write each equation in its equivalent logarithmic form. We still have to say what the base is. Okay, so in this case, the base, we don't see it as a subscript, we see it as the base of an exponent. So we have 12 squared equals x. It's the 12 that's going to move. Okay, so we're going to move it and have 2 equals, right? The 2 didn't move, it stayed on the left, it's just dropped down now and is not a superscript anymore. 2 equals the log of x base 12. On part B, think about what the base is. Think about where it's going to move and what it's going to look like. Pause if you need to. The b is the base, and we're going to move it and have 3 equals the log of 8 base b. And then part C, e is the base, y equals the log of 9 base e. We're going to talk about that base e log here in a little bit, but this is changing from exponential into logarithmic form. We're just doing and undoing each other. Okay, now we're going to evaluate. That's what objective 3 says. 3 says evaluate logarithms. And actually, we're going to be evaluating with objective 4 as well. We just have with example 3, we're going to see one type of how to evaluate, and then with examples 4, and I think example 5 as well, we're going to see some other methods of evaluating. Remember, evaluate just means to find the value of. All right, so let's talk about how to do this, and the idea is that we're not just punching buttons in a calculator and pressing enter. In fact, I can guarantee you on the problems you see in front of you, if you try to do the log of 16 equals, you are not going to get the right answer. Test me. I hope you will. See if you get the right answer. All right, so for the log of 16 base 2, okay, that's what we're going to go through first. The point for us is to rewrite part of this in exponential form. Actually, we're going to rewrite the expression in exponential form. But what we need to do that is an equation. So instead of saying the log 16 base 2 all by itself, I'm saying I'm going to make that equal a certain value. We don't know the value, so I'm just calling it x. You can call it whatever you want. Okay, so once we have it written as the log of 16 base 2 equals x, we can rewrite that. There is supposed to be an x power right there. Sorry about that. As 16 equals 2 to the x. It's a giant superscript, isn't it? There we go. Okay, so we have rewritten the log of 16 base 2 equals x as 16 equals 2 to the x. Now we're going to ask, can we rewrite these two sides to have the same base? Okay, it's all about that base. All right, so 16 is actually 2 to the 4th power. Okay, we know 16 is 4 to the 2nd power, but if we wrote this as 4 to the 2nd, we wouldn't have the bases matching. We need to think about it as 2 to the 4th. So if we say that 16 is 2 to the 4th, and that equals 2 to the x, then for these to be equal, the x has to be 4. So going back to the original thing, if x is 4, then that means that the log of 16 base 2 is equal to 4. All right, let me go through that process with you again. We set the expression equal to a variable. Then we converted the logarithmic equation into an exponential equation. We rewrote the bases. The 16 can be rewritten as 2 to the 4th equals 2 to the x. And if 2 to the 4th is 2 to the x, then the x has to be a 4. And so when we set up this equation to solve for x, the expression is equal to 4. I'm going to go through part B with you as well. Parts C and D, the textbook has also gone through these in a chart within 3-2. So you can check those out if you want to see the solutions for that. Okay, so the log of 1/49 base 7, and I've set this equal to x now. All right, so I want you to think about your next step based on the previous problem. I want you to pause if you're not done thinking. We're going to rewrite this as 1/49 equals 7 to the x power. We moved the base. Now, this question up here still applies. Can we rewrite the 1/49 and the 7 with the same base? I know 49 is 7 squared. So 1/49 will be 7 to the negative 2 power. And so 7 to the negative 2 is equal to 7 to the x. X is equal to negative 2. And the log of 1/49 base 7 is equal to negative 2. Because that's what we set. We set that equal to x earlier. Okay, parts C and D, again, you can check the textbook out for solutions for those. Okay, objective 4, use basic logarithmic properties. We're using basic logarithmic properties, but we're still evaluating. So objective 3, that umbrella could have been over objective 4 as well. Okay, we're going to talk about a couple properties. One of them is a basic logarithmic properties involving 1. Okay, there are 2 of these properties. One of the properties says you have a logarithm that equals 1. And that happens when you have a log of a certain number that has the exact same base. So the log of b with the base of b is equal to 1. The other logarithmic property involving 1 is when you're taking the log of 1. Okay? If you're taking the log of 1, the log of 1 with any base is equal to 0. And this does a nice job for both of these of explaining where they come from. It's that converting into exponential form. If you change number 2 into exponential form, it would be b to the 0 equals 1. Well, anything to the 0 is 1. So the logarithmic form, inverting that, well, changing that to logarithmic form would have the same thing going on. And the log of b base b is 1 because b to the first power is always going to be b. Okay, those are 2 rules for us to memorize and to use. Here's example 4, using properties of logarithms. The log of 7 base 7 is 1 because the 7's match. The log of 1 base 5 is 0 because you're taking the log of 1. That value will always be 0, regardless of your base. Okay, the second set of properties is called the inverse properties of logarithms, and it also has a canceling out kind of effect. Okay, so for this one it says if you have the log of b base b to the x, instead of saying it equals 1 when there wasn't an exponent, now it's just going to equal x. The log of b base b to the x is equal to x. And the same goes if you have b to the and the log base b is in your subscript, this is also equal to x. So with example 5, use the inverse properties of logarithms. The log of 4 to the 5th base 4 is equal to 5. And 6 to the log 9 base 6 is equal to 9. Yes, it's that simple. And no, you don't have to have any work. But you should be able to cite the inverse property of logarithms to justify what you're doing if you're asked to do that. Okay, now let's talk about graphing logarithmic functions. Example 6, graphs of exponential and logarithmic functions. So we can't seem to get away from exponentials. This is why they have the same chapter, exponential and logarithmic functions. They go together. Okay, so if we are going to get a graph of g of x equals log x base 2, we're actually going to get that from f of x equals 2 to the x. You saw this in 3.1 when you had to graph a parent function using a table and then use what you know about transformations to get the new graph without going through the process of making a table on your own. This is the same basic kind of thing. We have a transformation-ish going on here. Okay, so the graph of f of x equals 2 to the x, you'll make a table for that. And this is just like you did in lesson lesson 1. Okay, if x is negative 2, then we have a 1/4. If x is negative 1, then f of x is 1/2, and 0, 1, 1, 2, 2, 4, 3, 8. Just substituting our x into f of x. All right, and this is what the graph looks like. Okay, now, a logarithmic function, remember, is an inverse. And if it's an inverse, that means that we have to switch x and y and solve for y. As far as the table of an inverse goes, we just reverse the coordinates or switch the x's and the y's. So instead of having 3, 8 on f of x, we have 8, 3 on g of x. The graphs will look like they have been reflected over this line y equals x that I'm showing there. And here's the full graph. The blue is the f of x, and that purplish raspberry color, that is your g of x. That's your logarithmic function. Okay? I want you to notice a couple things, and the next slide will have us looking at that too. F of x has a horizontal asymptote. Its range is 0 to infinity. On the other hand, when we invert that, when we switch the x and the y, g of x, the logarithmic, does not have a horizontal asymptote. Instead, it has a vertical asymptote. And instead of its range being 0 to infinity, its domain is 0 to infinity. Does that make sense? We switched x and y. So the range for exponential becomes the domain of the logarithmic. And the domain of the exponential, negative infinity to positive infinity, becomes the range of the logarithmic, negative infinity to positive infinity. Okay? All right, this next page will have us look at that as well. So, it's showing you here that the horizontal asymptote y equals 0 for the exponential becomes the vertical asymptote for the logarithmic. The ordered pair 0, 1 becomes the ordered pair 1, 0. Okay? Here, this would be a decay function, but still the horizontal asymptote becomes a vertical asymptote. And the ordered pair 1, 0 is now the ordered pair 0, 1. All right, so some neat things go on with exponentials and logarithms. Promise you guys we're almost done. This is just a big section. Feel free to pause and say, I need to come back to the graphing part later. Okay, I wanted to show you something within this lesson 2 that you saw back in lesson 1. Okay, we had this chart in lesson 1, characteristics of exponential functions of the form f of x equals b to the x, and we have this chart in lesson 2, characteristics of logarithmic functions of the form f of x equals the log of x base b. I want you to see in here this is going to be really wordy. Okay, really wordy. But number 1 for exponentials, talking to you about what I just said. The domain was negative to positive infinity. The range was 0 to infinity for an exponential. If we go over and trace that to the logarithmic, they are switched. The domain is 0 to infinity, and the range is negative to positive infinity. The second set of characteristics, this says that the y-intercept is 0, 1, and the y-intercept is 1, and there is no x-intercept, if we switch those for a logarithmic, the x-intercept is 1 over here, but there is no y-intercept. We're switching things. For the third one, b has to be greater than 1. And if b is greater than 1, we have an increasing function. Same goes for logarithms. If b is greater than 1, we have an increasing function. If b is between 0 and 1, we have a decreasing function. Okay, so 1, 2, 3, they just parallel each other perfectly. With the exponentials, the exponential throws in a 5 that the logarithmic doesn't, and it says f of x is b to the x. It's 1 to 1 and has an inverse that is a function. Okay, we could have had number 5 in the logarithmic as well, because logarithms and exponentials are inverses of each other. But they jump straight to 5, which is a mirror of 6 that says the exponential will approach but not touch the x-axis, so we have this horizontal asymptote. Over here, we approach but do not touch the y-axis, so we have a vertical asymptote. Notice this arrow notation that's going on. As x approaches 0 from the positive side, the log value is either going to approach negative infinity or it's going to approach positive infinity. Okay, transformations are coming back. Transformations are not going to go away from us. But you need to feel good about the fact that they stay the same from function to function, from absolute value to polynomial, even linear, even though it's kind of hard to see with linear, square root functions, exponential functions, now logarithmic functions. So if you're going to have a vertical translation, if you add or subtract outside of the function, in this case outside of the logarithm, okay, going to shift the graph upward if we add, going to shift it down if we subtract. If you add or subtract inside the logarithmic function, you have a horizontal translation. It's still the opposite of what you expect it to be. Okay, so if it says plus c, we've shifted left. And if it says minus c, we've shifted right. Okay, notice the vertical asymptote mentioned within those boxes. One thing I want us to focus on that we didn't focus on as much with the polynomials is the idea of reflection, but it is really important, and you saw it with exponentials and you're going to see it with logs. If the negative is multiplied outside of the log, that means it's a negative log, then we have a reflection over the x-axis. That means it's going to take your logarithmic function and it's going to flip it down. Okay? If the negative is multiplied inside the log, it's going to take your log and it's going to flip it over the y-axis. Okay, so we have these reflections if you have a negative multiplier. Vertical, horizontal translations, and reflections. Those are the top 3 reflections. We also do vertical, stretch, and shrink. But as far as the heavy hitters, vertical, horizontal translations, and reflections are those heavy hitters. Okay, multiplier outside will stretch it vertically, and a multiplier inside will stretch and shrink horizontally. Again, inside is always opposite of what you think. A c greater than 1 actually shrinks or compresses the graph. A c greater than 1, or between 0 and 1, actually stretches it out. Okay, let's talk domain. Find the domain of a logarithmic function. The domain is based on where's the asymptote and which direction is this logarithmic function headed when we graph it. Okay, so we're going to base this off of f of x equals the log of x base 4. This has a domain from 0 to infinity. Notice the 0 is non-inclusive because x equals 0 represents a vertical asymptote. If we change that to the log of x plus 3 with this same base 4, the plus 3, you need to notice, okay, that's an adding inside, so we're shifting to the left 3 units. So that's going to move our domain left 3 units. Okay, let's go on to common logarithms. Common logarithm, remember, is a log base 10. If you ever see a log with no stated base, or if you ever write log and you do not put a base, it is automatically base 10. Even if you know it's not supposed to be base 10, if you don't write it, it's base 10. Common logarithm. Okay, so we look at this thing modeling the height of kids, and you're given a function. X is how many years old they are. We want to know the approximate height of the child when they're age 8. Okay, so age 8 would mean, let's substitute 8 in for our X and then use our calculators to calculate this. The log button on your calculator is a base 10 log. Okay, so this, I'm not going to go through it. You can see the calculations in your books. The properties that we talked about for base B logs earlier, the properties involving 1 and the inverse properties still apply to common logs. Log of 1 is 0, log of 10 is 1, so long as the base is 10. Log of 10 to the x is x, and the 10 to the log x power is still x. We also have natural logs. Natural logs, we saw this at the beginning now like 25 minutes ago, where we had this base e. Okay, e, remember, is a number that is found naturally in finance, in population growth, in radioactive things as far as exponential growth and decay. We see this e in nature. A log with a base of e is a natural log ln. I always make my L cursive when I'm writing myself so that it doesn't look like a 1. But anytime you see an ln, that's natural log, and it's log base e. The domain for natural log, it's exactly the domain for any other log. We need to figure out how far and which way has this been scooted. Okay, one way we can do that is, instead of just looking at it, we can set up an equation with what's inside the log. 3 minus x has to be greater than 0. We cannot take a log or a natural log of a value that's bigger than 0. Or I'm sorry, that's less than or equal to 0. So to find the domain, we set this greater than 0, and then we solve. So 3 is greater than x, or x is less than 3 would be our domain. That would be your answer. For part B, it's just going to be x minus 3 is greater than 0. So x is greater than 3 is our domain. Okay, those would be the x values that would produce y values if we were going to graph this. The properties for natural logarithms are the exact same properties that we've had all along for common logs and for general logs. I think this is the last example, and I'll let you go. This was a marathon today. Now we have a function that involves a natural log. Same process as a couple of examples ago. You have a function, we're told that x is measured in minutes, and we want to find the temperature if 50 minutes have gone by. So we're not just looking at the chart. If you read this, it's asking you, how does the model compare to the chart? We're not just going to look at the chart, but we want to know, what does the model say about 50 minutes out? And if you do f of 50 using the ln button on your calculator, you're going to find that that's approximately 41. If we check that with the chart, 50 minutes out, 41 degrees, this is temperature increase in an enclosed vehicle, good problem for the summer, then we can see that the model matches the chart very, very well. All right, so your Math Excel assignment has been opened, and it will stay open until, I believe it's Wednesday morning. Check the due date on it, though, to be sure. I've set it so that you can score after the due date, but your questions that you do after 8:16 on the morning of the due date will only count for 50%. So make sure you get as much as you can done, preferably every single problem done before that due date.